Hello, this is the 21st video on my multivariable calculus course. In this video, we're going to talk about triple integrals in cylindrical coordinates. As seen in the last example that we did in the previous lecture, when projection of the solid E onto the xy plane is a polar region, we can use polar coordinates for the region that is projected onto the xy plane. So what does that mean? It means we do dz followed by r dr d theta. This is in fact using a new coordinate system called cylindrical coordinates. So what are cylindrical coordinates? So it's basically a three-dimensional version of polar coordinates. So if you take a point which is x comma y comma z, we can assign three numbers to this point called r, theta, and z. So what are the three numbers? Well, r is the distance to the origin. If you drop the perpendicular from the point and call that one h, so that's r. Theta is the angle that it makes with the x-axis, and z is the same z. So x is r cosine theta, y is r sine theta, and z is the same z as in Cartesian coordinates. R is always greater than or equal to 0. Theta is between 0 and 2 pi. And of course, z could be any real number. So this is generally the limits of these three variables. Every point in the three-dimensional space can be represented by r, theta, and z. And we talked about that just now. The variables r and theta represent polar coordinates of the projection of each point on the xy plane. So now we will do some examples. Find the volume of the solid in the first octant inside both cylinders x squared plus y squared equals 1 and x squared plus z squared equals 1. So the first thing, as usual, is to draw the diagram. We have x, y, z. They said it must be in the first octant. So if we look at the first octant, it is everything that x, y, and z are positive. So we can ignore the portions that x, y, or z are negative. X squared plus y squared equals 1. That is a cylinder. And they told us only the portion that is positive. So I can ignore the portion that is below the xy plane, or the portion that x is negative or y is negative. So I only get the bottom is only a quarter of a circle. So this is x squared plus y squared equals 1. Next one is x squared plus z squared equals 1. So if I draw that one, I would get a cylinder also in this direction. So this portion is outside of the region, so I'm going to erase that. And also this portion is outside of the region, so I'm going to erase that one as well. So we really are going to get this solid. And this solid, in front it's a cylinder, on top is also a cylinder. So there is a crease here. So this is like kind of a crease here. So let me use dotted lines for that one. So this is the crease. And on this side we have a cylinder, so like this. Hopefully it makes it a little bit more clear. And on top we also have a cylinder like this. So in order to write down the volume of this, we'll have to relate the volume with a triple integral, and then we'll have to evaluate that triple integral. So let's say this solid is E. Let's look at the projection onto the xy plane. Well, the projection onto the xy plane is a quarter of a circle. So the radius was 1, so it's a quarter of a unit circle centered at the origin. So this is the projection. Now looking at this region, well, do we have a top for the solid? Well, we do have a top for the solid. The top is z equals, so we'll have to evaluate z from the cylinder. So this cylinder is the top. So the top is z equals root 1 minus x squared. And the bottom is z equals 0, and the projection onto the xy plane is a quarter of a circle. So it's like a quarter of a disk, if I were to be a little bit more precise. So this is our region. Now, since the projection onto the xy plane is a polar region, it is best to use cylindrical coordinates. So volume of E is equal to triple integral over E of 1 dV. So by what we have talked about before, because triple integral of density, it gives you the total mass. And if the density is 1, mass and volume are the same. So now, since we have a top, we have a bottom, and we also have the projection onto the xy plane as a polar region, we will use the cylindrical coordinates. So the integrand is 1, so we can ignore that. That doesn't need to be changed to polar coordinates, cylindrical coordinates, because 1 is already in cylindrical coordinates. Now dv would have to be replaced by r dz dr d theta. Next, we're going to have to write down the limits of z. So what are the limits of z? They're from bottom, which is 0, to top, which is root 1 minus x squared. However, we have to evaluate that in terms of r and theta. So x squared is r squared cosine squared theta. So those are the limits of z. Then limits of r, can be obtained by looking at the region R. So the limits of R are 0 to 1, and limits for theta are from 0 to pi over 2, because we have a circle that is centered at the origin, but it's only quarter of that circle. So this is our projection onto the xy plane. So theta would be from 0 to pi over 2. Okay, and this is the setup of the volume. The rest is evaluation of the integral. So we're going to go ahead and evaluate this integral from 0 to pi over 2, from 0 to 1. Well, first one is dz, so we'll have to evaluate that. We'll get r is a constant, so that would be just z times r, from z equals 0 to z equals root 1 minus r squared cosine squared, and then dr d theta. We'll plug in z equals that square root, so we get 0 to pi over 2, 0 to 1, and that gives us r square root of 1 minus r squared cosine squared theta dr d theta. So now how do we evaluate this integral? Well, to evaluate this integral, we need to do a u sub for this one, because derivative of this is 2r cosine squared, so which is right here. So r is right here. So we'll do a u sub for 1 minus r squared cosine squared theta. So this gives us du is equal to minus 2r cosine squared theta dr. And we are doing the integration with respect to r. Okay, so integral from 0 to pi over 2. Integral, okay, so if r is 0, we get u is 1. And if r is 1, we get 1 minus cosine squared of theta. We will have to change the limits of integration in order to have the equality to be valid. Then we have square root of u, and then we have r. So what is r? R is negative du over 2 cosine squared theta. So I'm evaluating dr from here, and then d theta. So let's now evaluate this. So what do we get? We are going to get integral from 0 to pi over 2. Integral of, and this is d, yeah, there's already a du here. So integral of root u is going to be u to the power of 3 halves divided by 3 halves. So that's integral of root u. And then this is from 1 to sine squared of theta. And of course, there's also a negative 1 over 2 cosine squared of theta, and then d theta. So next, we're going to have to plug in the values. So what do we get? We get 0 to pi over 2. Plug in the values. Sine squared would give us sine cubed theta. And then we are going to write it down as 2/3. So 2/3 sine cubed of theta. And then minus, when you plug in 1, we get just 2/3. And then multiply it by negative 1 over 2 cosine squared of theta d theta. Next, we're going to have to evaluate that in terms of d theta. So this is integral from 0 to pi over 2. Let's multiply this out. We get negative sine cubed of theta divided by 3 cosine squared of theta, and then plus 1 over 3 cosine squared of theta. So we'll have to break this up into two different integrals. So this is integral from 0 to pi over 2 minus sine of theta, sine squared of theta over 3 cosine squared of theta. So you'll notice that I can write down sine squared as 1 minus cosine squared, and then everything is in terms of cosine, and the derivative of cosine, which is negative sine, is right there. So this is the first integral. The second integral is integral from 0 to pi over 2 of 1/3 secant squared. What is integral of secant squared? Well, integral of secant squared is just tangent. So we can evaluate that one as tangent. So, and then what is the integral of the other one? We can do that separately. So this is integral from 0 to pi over 2. So if you do a u substitution for cosine, so we're going to do a u substitution for cosine. So we're going to get du equals negative sine theta d theta. So this gives us minus or 1 minus u squared over 3u squared du. This is when you substitute u equals cosine. Now cosine of 0 is 1. Cosine of pi over 2 is 0. So this is the first integral. And the second integral is going to be 1/3 derivative of tangent is in fact um, secant squared. Okay, so let's see what we get from here. The first one gives us 1 over 3u squared, so that's negative 1 over 3u. And the next one is minus 1/3 times u. And this one is from 1 to 0 plus 1/3 tan of theta from 0 to pi over 2. Unfortunately, if you plug in pi over 2, you get infinity. So that can't be done. Instead, what we can do is we can write down everything in terms of theta and then plug it in to see what we get. So we'll have to like basically take the limit. So this would be minus 1 over 3 times u. What was u? U was cosine of theta. So that's what we get. And then plus, I'll just put this one in here, plus 1/3 tan of theta. And this goes from 0 to pi over 2. But the other one I can plug it in. So minus 1/3 times 0 plus 1/3. So let's see what we get for the first one. The first one is negative 1 plus, if you write down tangent as sine over cosine, we get sine here and then 3 cosine of theta here from 0 to pi over 2 plus 1/3. Okay, now at 0, we are easily able to evaluate that. At pi over 2, we'll have to take the limit. So we'll have to take the limit as theta approaches pi over 2 of minus 1 plus sine of theta over cosine of theta, 3 cosine of theta. So that's at pi over 2. Minus at 0, we get minus 1 plus 0 divided by 3 and then plus 1/3. So let's take the limit of the first one as theta approaches pi over 2. For the first one, we'll have to take the derivative. We have to use the L'Hopital's rule. We get cosine of theta on top because when you plug in pi over 2, minus 1 plus sine of pi over 2 is 0 over cosine of pi over 2, which is also 0, minus 3 sine of theta. So if we use L'Hopital's rule, we get this plus 1/3 which is 2/3. And when we plug in pi over 2 here, we get 0. So cosine of pi over 2 is 0, sine of pi over 2 is 1, so we get 2/3. So the answer to this problem is 2/3. Okay, so let's move on to the next problem. Let E be the solid under the cone this inside the surface x squared plus y squared equals 1 above the xy plane, and we place an object whose mass density at every point is the distance to the xy plane, and we want to find the total mass of the object. So the very first thing is to draw the diagram for this and set up the integral, turn it into an appropriate coordinate system, and then evaluate the integral. So let's do that. So it's the solid under this cone. So we'll draw the cone first. So we have x, y, z. The cone is vertex at the origin inside this cylinder. So it's inside the cylinder here. So it is something like this. And they also told us that it is above the xy plane. So this is basically the region we have. So we have the cylinder, and uh, we have basically removed a cone from the cylinder. And once we look at the intersection, we realize that this point is 1. So z equals root x squared plus y squared, and x squared plus y squared equals 1 gives us the intersection as x squared plus y squared equals 1 and z equals 1. So this point is exactly 1. So let's call this region E. Let's find out the projection onto the xy plane. So what is the projection? The projection is a disk of radius 1 centered at the origin, which I generally denote that by R. So let's call that R. So this is R. Now looking at the region, is there a top for the solid that they gave us? Well, the solid does have a top. The top of the solid is the cone. So I'm gonna write it down right here. So the top of the solid is z equals root x squared plus y squared, and the bottom of the solid is z equals 0. What is the projection onto the xy plane? The projection is a disk, so which is a polar region. So what does that mean? It means it is best to use cylindrical coordinates. So we can turn this one into z equals r and then use cylindrical coordinates. So now the next thing they said is that an object whose mass density at every point is the distance to the xy plane. So if you take a point here, we want the distance to the xy plane. So what is the distance of a point to the xy plane? Well, that's the z coordinate. So the density is z. Now we want to find the total mass of this object. So the total mass is the triple integral over this region of the density dv. Now we'll have to switch to cylindrical, which we will do. So r dz dr d theta. We'll have to find the limits of z. So limits of z are from the solid, from the first diagram that we have. Top is r, bottom is 0. So it would be 0 to r. Limits of r are from the projection, so 0 to 1, and limits of theta, 0 to 2 pi. And then we will evaluate the integral. So 0 to 2 pi, 0 to 1. So next we'll have to evaluate this one dz. So zr dz would be z squared r over 2 from z equals 0 to z equals r. And then dr d theta. 0 to 2 pi, 0 to 1. When we plug in r, we get r cubed over 2. And when we plug in 0, we get just 0. So this gives us integral from 0 to 2 pi. Integral from 0 to 1 becomes r to the 4th over 8 from r equals 0 to r equals 1, and then d theta. Integral from 0 to 2 pi. When you plug in 1, we get 1/8, and when we plug in 0, we get 0. And this would become 1/8 times 2 pi. So the answer is pi over 4. Okay, let's move on to the next example. Find the volume of the solid that lies above the surface z equals r and inside the surface given by x squared plus y squared plus z squared equals 1. So first we have to identify the surface that they gave us. Z equals r is z equals root x squared plus y squared, which is a cone. And the other one is clearly a sphere. So it is inside the sphere and above the cone. So let's draw a diagram. So it's inside the sphere with radius 2 centered at the origin, and it is also above the cone. So it is something like this. Now, which region is really relevant? The region that is relevant is not underneath the cone. So I can erase this one. So it's really basically like something like this is the region. So you can think about that as like basically an ice cream cone. So I'm going to erase the parts that are not relevant, and this is what we have. So we want to find the volume of this solid. Let's call the solid E. We will find out what's the top, what's the bottom, and we'll also find out what's the projection onto the xy plane. So what is the top? The top is the sphere. So we will solve x squared plus y squared plus z squared equals 4 for z. So we get z equals root 4 minus x squared minus y squared. I'm only going to look at the top part. That's why z is positive. So I don't have the plus minus. So that is the top. And what is the bottom? The bottom is the cone. So let me write this down. 4 minus x squared minus y squared. And what is the bottom? The bottom is the cone z equals r. Now let's also find the projection onto the xy plane. Projection onto the xy plane is the intersection of the two objects. So intersection of the cone and sphere. So let's write it down. So we have z equals r, and we also have x squared plus y squared plus z squared equals 4. So this means if I take z equals r, plug it at the bottom, I get r squared plus r squared equals 4. So that gives us r equals root 2. So the projection is in fact a disk of radius root 2. So this is the projection. Okay, so now given that the projection is a disk of radius root 2, we realize that it is best to use cylindrical coordinates, or at least it might be the best to use cylindrical coordinates. So this is the projection. So notice that the projection is the widest part of the solid. So now we can write down the volume. So what is the volume? First of all, the volume is always equal to the top triple integral of 1 dv over the solid. Next, we notice that it's best to switch to cylindrical, so we'll do that. R dz dr d theta. Limits of z are from bottom to top. Bottom is r because it's the cone, and top is the sphere. So the sphere is root 4 minus x squared minus y squared, but since we are using cylindrical, we'll have to switch to cylindrical. So it's root 4 minus r squared. Okay, so that's good. Next, we're going to do the limits of r, so that's 0 to root 2, and limits of theta are from 0 to 2 pi. And then finally, we'll have to integrate. So integral from 0 to 2 pi, integral from 0 to root 2. So when we integrate this one with respect to z, we get zr, and this is from z equals r to z equals root 4 minus r squared dr d theta. Integral from 0 to 2 pi, integral from 0 to root 2. When we plug in z equals root 4 minus r squared, we get r times root 4 minus r squared minus r squared dr d theta. Okay, so now the first one, if we look at this guy, the derivative of this one is 2r, which is right there, or negative 2r, which is right there. So we can use u substitution. So if we do u equals 4 minus r squared, we would get this integral from 0 to 2 pi. The first one becomes integral. So du is going to be negative 2r dr. And this gives us root u and then du over negative 2, because dr is du over negative 2. Although really at this point, you probably should be able to do these integrations without u substitution. So we get 0 when we plug in r equals 0, and when we plug in r equals root 2, we get 2. So this is the first integral. The second integral is very easy to evaluate. That's r cubed over 3, and this one is from r equals 0 to r equals root 2, and then d theta. So we're going to plug in the values. We get 0 to 2 pi. Integral from 0 to 2 of root u is u to the power of 3 halves over 3 halves. And there's also a negative 2 at the bottom. And this is from 0 to 2 minus, if you plug in root 2, we get 2 root 2 over 3. And if you plug in 0, we get 0. Okay, so now everything here is constant. When we integrate, we get this constant times theta. So we get negative 3 at the bottom here. And then we plug in 2, we get 2 root 2. And then 0 gives us 0. And then we get minus 2 root 2 over 3 multiplied by 2 pi. So that is going to be the answer. So negative 4 root 2 over 3 times 2 pi. Okay, so something doesn't quite add up because what I got here is a negative number, and the answer should not be a negative number because it is a volume. So this is something we'll have to double check to make sure we have done everything right. There's something not quite right about this. So we went from r all the way to root 4 minus r squared. So that seems correct. And when we integrated, we got zr. We plugged in root 4 minus r squared. We plugged in r. So that's good. So root 4 minus r squared, that's root u divided by negative 2. And that gives us that. Okay, so when r is 0, we are going to get u equals 4. Okay, so that's what is wrong here. So this would have to be from 4 to 2. Okay, so the wrong answer gave us an indication that there is something wrong here. So we'll fix that. So when we plug in 2 here, we get 2 root 2 over negative 3. So that's that. And then minus, when we plug in 4 here, we get root 4, which is 2 cubed, that's 8 over negative 3. And then minus 2 root 2 over 3. And all of that times 2 pi. So we can solve this one. So this one is 8 minus 4 root 2 divided by 3 times 2 pi. So this is the volume, and this one is in fact a positive number. Okay, great. So let's look at the next example. Evaluate this triple integral where E is the solid that lies above the plane z equals 1 and inside the sphere. So again, we're going to draw the diagram. So we have a solid that lies above the plane z equals 1 and inside the sphere. So sphere is radius 2. So we're looking at this. Okay, so really everything that matters is this portion. So this is RE. Well, let's first evaluate the top of this. So the top is the sphere. So the top is z equals root 4 minus x squared minus y squared, which is root 4 minus r squared. So that's the top. What is the bottom? The bottom is z equals 1. And again, we have to find the projection. So the projection would be the intersection of these two things. So z equals 1 and x squared plus y squared plus z squared equals 4. So let's take the intersection of these two. We get x squared plus y squared equals 3. So this is a radius of this is a circle of radius root 3 centered at the origin. Okay, and this is our region, which is here. It's right here. So this is our region. And what we can do is we can use cylindrical coordinates. Why? Because the projection onto the xy plane is a polar region, and there is a top, there is a bottom. Top is a function of xy, bottom is a function of xy. So let's see what they asked us to evaluate. They asked us to evaluate the triple integral of z. So a triple integral of z dv over e is equal to triple integral. We'll switch to cylindrical based on the discussion that we had. So z r dz dr d theta. So let's first look at the limits of z. Bottom is 1, top is root 4 minus r squared. So 1 root 4 minus r squared. What are the limits of r? From the diagram, 0 to root 3 and theta 0 to 2 pi. So limits of r come from the projection. Limits of z come from the diagram for e. And the rest is evaluation of these integrals. So this is integral from 0 to 2 pi, integral from 0 to root 3. So integral of z is z squared over 2. And this one we have to substitute z equals 1 to z equals the square root, which fortunately gets rid of this square root. We get integral from 0 to 2 pi, integral from 0 to root 3. If you plug in root 4 minus r squared, we get 4 minus r squared times r and over 2 minus, when we plug in 1, we get r over 2 dr d theta. So if we plug that in, we get integral from 0 to 2 pi, integral from 0 to root 3. This is 4r minus r cubed minus r over 2 dr d theta. So 4r minus r, that's 3r. So we get integral from 0 to 2 pi. That's 3r squared over 4 minus r to the fourth over 8 from 0 to root 3 d theta. And I have only one variable here, so which is why I didn't indicate which variable is evaluated, although I will do that just to be more clear. So this is integral from 0 to 2 pi. If we plug in root 3, we get 9 over 4 minus 81 over 8. And if we plug in 0, we just get 0, d theta. And all we got to do is to multiply this by 2 pi. So we get 9 over 4 minus 81 over 8 d theta, which is 2 pi. And this would be our final, sorry, this is actually 9 over 8. Because when you square root 3, you get 3. Square that, you get 9. So that's 9 over 8. So this would in fact be 9 over 8, which can be simplified. This is just 9 over 8. So this is 9 over 8 times 2 pi, which is 9 over 4 times pi. So this is our answer to this problem. So to summarize what we did today in this video was we learned how to use cylindrical coordinates. And the way you want to do that is to draw the solid E, draw the projection onto the xy plane, write down the integrand in terms of r, theta, and z, replace dv with r dz dr d theta, find the limits of z by looking at the region, by looking at the solid E. Top would be upper limit of integration, bottom would be lower limit of integration. Then you look at your region R, and then you find limits of R and theta from that region. So to summarize, this is the formula. So I will see you in the next video.